Hello class, in this video we are going to continue with the exercise session and we are going to solve problems 1, 2, 3, 4, 5 and 6, page 52 in the book. So please open up your books and follow up with me. So we are going to start with problem 1. Problem number 1, it states that in a hurricane, a bolt of lightning is accompanied by a transfer of a charge of 20,000 coulombs. So we have a charge, so Q. So in this hurricane, a bolt of lightning is accompanied by a transfer of charge, and the Q, or the quantity of this charge, is 20,000 coulombs. And that transfer of charge is between the Earth and the cloud. And this lightning holds for 1.2 seconds. So the time of transfer is 1.2 seconds. The question is, what is the current produced assumed constant? So we are going to assume that the current throughout this 1.2 second is constant. What is the current produced with this given quantity of charge? We know that the formula of the electric current is that I equals to Q, quantity of charge, over the time T. Q is in coulombs, T is in seconds, so we're going to have 20,000 coulombs over 1.2 seconds, that is 16,666.67 ampere. This doesn't really look very neat, so we can use another way to write it. So we can say it is 1.67 times 10 to the power 4 ampere. Okay? Now that's a big quantity. Here, this is a very big quantity of charge. You might ask yourselves, why don't we harvest this energy from the lightning? Well, there are mainly two reasons. The first reason, so this is just a note. We might ask why, let me zoom in here, why don't we harvest the electricity or the electric energy from lightning? Well, basically, we don't do that for mainly two reasons, as I said. The first is that this big quantity of energy is supplied in a very short amount of time. As you can see here, 1.2 seconds. So even though the quantity of charge is very big, so C is very big, or the quantity of charge Q is very big, but the time T is really small. So this supply of energy is in a very short period of time. So if you want to actually store the total energy, it won't be that big of that big amount. We're not really supplying constantly 20,000 coulombs all the time, but we're only supplying 20,000 coulombs for 1.2 seconds. So that's a very short amount of time. That's the first reason. The second reason is that we don't really know where exactly and when exactly will the lightning strike, so we can actually build up the ways to store this quantity of energy, because build up the facilities. We don't really know exactly where it's gonna hit, so this increases the impracticality of storing the energy of lightning. Okay, so we don't know exactly when and where. Okay, that's just a note. Okay, now Let's move to question number 2. So first, question number 1, we were given the quantity Q, the time T, it's just a direct application. The current I is Q over T. Q should be in coulomb, T should be in seconds, the SI units. We divide them and we get the value 1.6 times 10 to the power 4 ampere. Okay, 1.67 times 10 to the power 4 ampere. This is the most exact one. This is like an approximate value, okay? Mostly an approximate value. Let's go now to exercise number 2. So, number 2, we have the circuit of figure 3.28. So this here is actually figure 3.28. Okay, we have this figure. We drew it here. It's here, and in this figure we have to find the current in the branches GB, BC, and DF, and finally in CF. What we have, like the given that we have, let me change the color. We have that the current, let me go inside here. So the current here passing through AH is 0.5 ampere, and we have that the current that's generated or supplied by the battery is called I, and we also have that the current passing through GF is 1 point, let me put it inside, sorry. So here through GF is 1.5 ampere. Now we have to find the currents IGB and IBC, IDF, and finally ICF. Let's start with IGB. So let me get the pointer. Let's start with IGB. So this current here. We know that the current passing here is 0.5 ampere, and the current passing here is 1.5 ampere. Okay? We have the law that at each junction, so at point G, the currents going in is this 0.5. So this 0.5 is going in. This 1.5 is also going in. So the summation of the two currents going in is the current going out, which is, or the current coming out, which is the current I. So IGB, let me write it here. IGB would be I, the one passing through HG, which is the same one passing through AH, which is just 0.5, plus the current here through GF, which is 1.5 ampere. What we are left with is 0.5 plus 1.5 is 2 ampere. So IGB is 2 ampere. Again, the current inside, or the current coming in is 0.5, another current coming in this junction is 1.5, the current going out is just I, and it is the sum of 0.5 and 1.5, that's 2 ampere. Okay, let's continue now with IBC. So IBC is the current here. Let's study the junction. So let me change the color, blue. So let us now study the junction B here. The current coming in is I. There is a current that is going out, which is this one here, the 0.5. we know that the current coming in is 2 ampere. We just studied that. And the current coming out is 0.5. So there's another current now, which is the one here. I'm sorry. So let me just write it here. The current coming in this junction is I. There's a current coming out, which is the 0.5 ampere. There's another current coming out here, which we have to find, which is the current BC, because this battery is supplying this current I. So when it's supplying here, the current will break down into two other currents, into the different branches, okay? So let me write it down in blue. IBC equals to the current coming in, which is I, which is 2, minus the current which is going out, 0.5. That is 1.5 ampere. Let me do it in another way. Choose a lighter blue. What happened exactly is that the current coming in, which is I, equals to the both currents that are coming out, IBA plus IBC. Okay, now IBA, we know that IBA here, it's just the same as IAH. So IBA is just the same as IAH. We know that it's the same branch, which is just 0.5 ampere. IBC is what I really don't know. And we know that I is 2 ampere. We just calculated from here. So what we're left with is that IBC would be equal to I minus IBA. Here it is, I minus IBA. Okay? So I is 2, IBA, which is the same as IH, 0.5. That's 1.5 ampere. Okay? Now, so we got the GB, we got BC, now we have to get DF. Do we have another given? Yes, we actually have another given. We have that the current passing here is 0.75 ampere. So let's continue. Yeah, and we have that the current passing, we have that the current passing here is 1 ampere. Now let's continue. We want to get now IDF. So we want to get the current passing through DF through here. Okay. Let's study. Let me choose another color. Green. No, a lighter green is better. Let us study this junction here, junction D. At junction D, 1 ampere is going in and 0.75 ampere is getting out. So there's a bit of this current that is going through this branch. So we know that the summation of what's going in is equal to what's going out. So 1 ampere here equals to 0.75 plus this one. Let's do the calculation here. So I want to get, we know that 1 IDF, right? IDF would be equal to 1 ampere minus 0.75. It's the same thing as what we did here. So 1 ampere minus 0.75 ampere, that's equal to 0.25 amperes. Okay? Again, let me repeat what we just did. The current going inside is divided into 2 branches. Okay? This one is 1 ampere. This one is 0.75 ampere. What's left for here? It's 1 ampere minus 0.75. So 1 minus 0.75, that's 0.25 amperes. So 0.25 amperes. Now, the last one, which is ICF. We want to find ICF here. The current passing through CF. Let us study. Which junction do you think we can study? Yes, that's right. We are going to study. Let me choose the color, purple, the junction C. Because look what do we have? We have the current going inside. We have the other current that's going outside, so this one is going outside as well. So this current here is divided into two currents, this one and this one. This current here is divided into these two branches, okay? This current here, the current BC, we already got that it's 1.5 ampere, okay? So BC is 1.5 ampere. 1.5 ampere branches into 1 ampere and something. What's this something? It's easy. So 1 ampere, 1.5 ampere is branched to 1 ampere. What's left for here is 1.5 minus this one, that's 0.5 ampere. Okay, so the current here branches into two currents. Here is 1.5, here is 1, what's left here is 0.5 ampere going down. Okay, let us write it down. What color I'm gonna use? Yeah, this one. So ICF equals to 1.5 ampere minus 1 ampere, we have 0.5 ampere. Okay, we just finished number 2, I'm sorry. Now we are going to do number 3 together. Okay, so number 3, let's read it together. In the circuit of figure 3.29, so this is figure, let us zoom in, this is figure 3.29, so 3.29. We have a charge, so a charge of 250 coulombs traverses the branch A and B. So the branch A and B is traversed by Q equals to 250 coulombs. And that is in time t, which is 125 seconds. Okay, and they are saying that, so in the branch A and B we have the charge 250 coulombs in 125 seconds in this branch, while in the other branch they connected an ammeter, and this ammeter is measuring a current passing through the A and B. So let me show you here. A and B. So in this branch we have current I, A and B, and the value of A and B is 1.5 ampere. Okay, the question is, what is the value of the current delivered by the battery? So we want to know the value of the current delivered by the battery. We know the current passing here, and we know the quantity of charge and time that this charge passed here, so we can know the current from the formula that we know about, and then we need to find the current supplied by the generator. Let us write down what we know. So the current supplied by the generator, this is plus and this is minus, is called I. We don't know the current passing here, but we know the charge and the time, and the current passing by this one here is 1.5 ampere, right? Let us do the calculation. Let us first find I, A, M, B. How can we find that? Super easy. We already have Q and T, and both of them is in the SI unit. So 250 over 1 to 525, that is, so 250 into 5, that is, let's see here, that's 2 ampere. That's 2 ampere. So we know now the current here is 2 ampere, the current here is 1.5 ampere. Super easy. At the junction A, the summation of the currents going out is the same as the current coming in. So we will gonna have, let me write down here, the current I equals to I A N B plus I A M B, and that is 1.5 ampere plus 2 ampere, that's simply 3 amperes. Okay, so the current here going in is divided into 2. We know that this one is 2 ampere, this one is 1.5 ampere, so I would be just 3 amperes. Okay, and we knew the current here from the charge and the time. Okay, now let's move to question number 4. We're gonna leave question number 4 for part 2 of the video, so we won't have like a very long video, so you can watch it in 2 fragments. Okay, in the second video